Hello, Chemistry 2342. We're going to continue our discussion of carboxylic acids and their derivatives. We're doing chapter 17-3, which is the preparation and some reactions associated with the carboxylic acids. So the first thing we're going to do is we're actually going to make some carboxylic acids by ways we've already done. So back in chapters 8, we were able to take double bonds and cut them in half using permanganate or ozone to create carboxylic acids. If these two R groups are the same, it makes two equivalents of one kind of acid. If these two R groups are different, it makes two different carboxylic acids, and you have to separate them. The other way to do that is to use ozone. Ozone will break that double bond and again create two carboxylic acid equivalents. If they're the same, it creates two equivalents of one acid, or if they're different, it doesn't for the two. Okay. The other reactions we can do with ozone involve the triple bond. So ozone can be used to clip the triple bond because those pi orbitals are much more susceptible to oxidation than other things. And so we could break that into, if we have a disubstituted alkyne, we can get it two carboxylic acids that can be the same or different. If we have a terminal alkyne, we end up oxidizing that last group here to CO2, and it typically goes away as a gas. Okay. So another way to do that is, let's look at this equation number 4 though. If you use ozone again, remember, benzene ring has the double bonds in it. And so the ozone attacks double bonds. And so what we end up doing is taking one of the carbons from the benzene and oxidizing all 5 of the other ones away to give it, and it goes away as CO2. But the alkyl group on the end is unhurt. And so we can actually end up with these alkyl carboxylic acids by oxidizing the benzene away. The other way to do it is if we have an alkyl group on the system here, we can actually, as long as there's benzylic hydrogens on this substituent here, we can oxidize that down and the rest of the chain gets oxidized away and we're left with this benzoic acid derivative of it. But it has to have these benzylic hydrogens here to make it oxidize. Okay. So we also learned about this in chapter 12 and 16 right here. If we have an aldehyde, we can further oxidize it down using the silver oxide right here. It's also called the silver mirror reaction because it creates silver 0 as the byproduct here, and it converts that aldehyde down to a carboxylic acid. We can also use permanganates on primary alcohols to give them down to the carboxylic acid as well. Again, it only works with primary alcohols. If you had a secondary alcohol, it would convert it to a ketone. Okay, so, and then once you have your aldehyde or your primary alcohol, you can use any of the Jones reagents, any of the chromium oxide reagents to convert it all the way down to the carboxylic acid. Remember, we have to use a different reagent if we want to stop it at the aldehyde. If we want to go from here to here, we can only use the PCC or the Swern. Okay, so one of the other interesting reactions we can do is we can actually do a nucleophilic addition to ketones using the cyanide ion. And the reason this works is we're actually doing something that we haven't done before. We can actually increase the length of whatever chain this is by 1 carbon to add this cyano group on here. And this is called a cyanohydrin because we have an OH here. And then we can take this nitrile group, which is a protected carboxylic acid, and hydrolyze it using acid to create a carboxylic acid that is 1 carbon longer than the original chain was here. So we have this alpha hydroxycarboxylic acid we make with this cyanohydrin reaction. So let me show you another thing down here is we can take any alkyl halide, as long as it's the primary, maybe a secondary, and react it with a cyanide as our nucleophile and then hydrolyze it down. But again, notice we're adding 1 carbon to the chain here. So if we had 5 carbons here, our product is going to have 6 carbons. So we're adding a single carbon to the chain that we can add that using that cyano group because it's a protected carboxylic acid. Okay, so we can also use the Grignard reagents with it. So if we have like a short chain and we can make a Grignard reaction out of it, we can react that with CO2. Remember, CO2 is basically just two carbonyls on the same carbon. And so we can have nucleophilic attack at that center carbon there to create the carboxylic acid first as the salt. And then when we acidify the reaction at the end, we get the free carboxylic acid. Notice that can be used to make any functional group here. As long as you can create the Grignard reagent, you can react it with CO2. So you can make primary, secondary, tertiaries, allyl, benzylic, or aryl derivatives of these things. So it's a very useful way to make a carboxylic acid system. Another way to do things is to actually, you can take any anhydride, acid chloride, amide, or ester, and by hydrolyzing them in the presence of acid, you can convert any of those groups back down to the bare carboxylic acid. The carboxylic acid is the most oxidized form of this, the most hydrated form of this. So you can hydrolyze any of those functionalized carboxylic acids down to carboxylic acid. So acid chlorides, esters, that's an anhydride, ester, amides, or nitriles can all be converted to that carboxylic acid. Okay, so now that we have, quote, our carboxylic acids, we know we can deprotonate them. And when we deprotonate them, we can use a variety of bases as long as the weaker acid is formed during the system. Now, because most carboxylic acids have pKa's around 5, that means we can actually use some pretty weak bases to be able to do this. For example, while you can't do this with alcohols, you can use bicarbonate, ammonia, carbonate can all be used to deprotonate a carboxylic acid to turn it into its salt right here. We can also use methoxide, hydroxide, ethoxide, or hydrate. All of these things can be used to deprotonate the carboxylic acid because they are significantly more acidic than the conjugate acid created during the reaction. Okay, and we learned about this before when we were looking at induction effects last semester, but here we can demonstrate that again. A regular acetic acid here has a pKa of just about 5 right here. By adding electron withdrawing groups here, that creates a more positive charge at your carbonyl, therefore increasing the acidity of this hydrogen. Adding 2 groups drops it all below 2. Adding 3 groups drops it almost down to a strong acid, almost down to a 0 pKa. So that's an inductive effect, and it affects the acidity of our system. So we can use that inductive effect to our advantage to make much more acidic systems. Okay, so now let's talk about reactions we can do. There's a carbonyl in the system, and so we can actually do some reactions with that. And as we've done with aldehydes and ketones, we've actually done a nucleophilic addition to the reaction to give us our nucleophilic addition products. And the reason this works is that once we get our nucleophilic attack, we can either have our incoming group leave or our outgoing group leave. In the case of an aldehyde or ketone right here, where we have a hydrogen or an R group right here, we end up with substitution. We end up with addition because neither hydrogen anion or carbon anion are good leaving groups. Okay, so what we end up with is addition reactions like we had with the in chapter 16. Okay, when we have leaving groups like hydroxide, chloride, alkoxide, or an amine, we end up getting what we call acyl substitution. In fact, these groups actually are good enough leaving groups that once we form this intermediate here, we have to look at which of these 2 groups is the best leaving group and whether it's going to leave or not. So we actually end up with another set of reactions called acyl substitutions. All right, so if we look at this reaction and the function of an aldehyde or a ketone, we would want the first step to be the attack of the nucleophile, creating this tetrahedral intermediate right here. This tetrahedral intermediate right here. And it does not have the hydride would be a leaving group here. Hydride is a very poor leaving group and rarely occurs. In the case of having a ketone, we would end up with an R- as our leaving group, which means it doesn't undergo the substitution reaction because no matter what the incoming nucleophile was, it would not do it. It only undergoes the s- addition reaction, not a substitution reaction. Now, this is different than if we have a carboxylic acid or other thing, because we can get what we call a nucleophilic acyl substitution reaction. So if we have a good leaving group, for example, L right here is a chloride, that makes a pretty decent leaving group as an acid here, and so we can end up with a substitution, not just an addition. And this works well for alcohols, esters, acid halides, and the acids and the amides, because our leaving group ends up being a neutral species. So the first step in the reaction is, of course, the attack of the nucleophile to the carbonyl, giving us the intermediate here. And then what we have is our proton from our nucleophile can transfer over to the leaving group, making it a protonated species, such that when it leaves as a neutral species. This is very important because that when it can leave as a neutral species, that makes it a great leaving group. And so that allows us to have our nucleophile come in and attack and give us our leaving group. So the only thing we really have to worry about now is what is the better leaving group, okay? And the better leaving group typically is always related to the weakest base, okay? So if we want our leaving group to leave as a neutral species, we're gonna do that proton transfer, but we also want things to leave as our weakest base. As such, if we look at our series here, HCl versus acetic acid, HCl is the stronger acid, which makes it the weaker base. Then we have a carboxylic acid or an alcohol. This is more acidic, making this the weaker base. Then we have alcohol and water, approximately the same pK. And then we have our amide as our strongest base. What that means is because the chloride is our weakest base, it means our acid chloride is most reactive, followed quickly by our anhydride. Okay, note both of these react with air, with water at room temperature. It doesn't take any additional catalyst or heat to make it happen. So once we get to our carboxylic and our esters, these take a little more trouble to get to go, and that makes our amides really, really stable. So that's why we sometimes use them as reactants and as solvents in reactions where we don't want them to be converted. Okay, so again, we're looking at, we can do a new reaction here, which is an acyl substitution, where we can displace the more reactive species with a less reactive species. So for example, you can make an amide from an acid chloride right here, but it's almost impossible to make an acid chloride from an amide. You can make an acid chloride from a carboxylic acid, but not by acyl substitution, by a different reaction where you're reacting with a sulfur compound that makes it a better leaving group. And we'll talk about that in the next set.